Here's a quick way to visualize point groups. Imagine you have a ring, and on it you do copies of a letter, like say the letter L. If you have the letter L there, then what you've created is CN symmetry. It doesn't have any mirror reflections, it doesn't have any other rotations beyond the main one. And so if you imagine the letter L on a strip, that's an example of CN symmetry. What about CNH? You're adding a horizontal plane, what they call a sigma sub h. So if you replace it with the letter E, that will actually have that symmetry. CNV means you have n vertical planes. So if you use copies of, say, the letter A, that would be CNV symmetry. If we're going to construct SN, I need something. For SN, I couldn't find a simple shape, so we'd have to use something like the letter R, followed by the letter R upside down, followed by letter R right side up. So you see it has to be an even number in order to have this symmetry at all. If n is an odd number, you're just doing a repeat of CNH. Now, what about DN? You use the letter S, because what you have here is simply a ability to rotate, but you can't reflect. There are no reflections here because the reflection of an S is a backwards S and you can tell the difference. So reflections are not a symmetry of DN, but a 180 turnover is. What about DNH? Well, there you've got more symmetry. In fact, you have letters like H or I, because that's going to give you both vertical planes and a horizontal plane of symmetry. DND is a trickier one. I use the letter N followed by a backwards N. So again, it has to be an even number. What makes that different from DNH? It has rotation symmetries and it has vertical reflection planes. It does not have the horizontal reflection plane. And more to the point, if you draw the mirror planes that you can vertically reflect in, and then you also draw the axes that you can rotate 180 around, these are not the same. They're not in the same place. In the case of DNH, the rotation and the mirror flip are in the same place. But for DND, they're in different places. So that is DND. Now that's about as far as we can go with just imagining one primary ring. The C infinity V is actually just a linear molecule, but one that isn't up-down symmetric. And the D infinity H is a molecule that is up and down symmetric and linear. So XAX or OO, whereas C infinity V might be HCN. Finally, we come to the polyhedral groups. We've got the tetrahedral group, which is the rotations of a tetrahedron. We've got TD, which adds in the reflections of a tetrahedron. So this has 12 elements, this has 24. TH I put in a different column because this is supposed to be the tetrahedral rotations, but with inversion added. But inversion is not a symmetry of a tetrahedron, so it's kind of a misnomer. What TH really is it's a subgroup of OH. You're swapping corners of a cube that are in the tetrahedron from the corners of the cube that are not in the tetrahedron. And O is the octahedral group, the rotations of a cube. I is the group of rotations of an icosahedron. Buckyball shares the symmetry of an icosahedron, though it isn't one. Now, you can also have versions with H, which includes inversion. So in the case of icosahedron, this has 60 elements and this has 120. This has 24 elements and this has 48. And those are all the point groups.